Today we're going to look at inverse relations and functions. Recall from chapter 2 that a relation is a set of ordered pairs. So on your note sheet, you can jot that down, that a relation is a set of ordered pairs. We know that ordered pairs, in each ordered pair there's always two parts to it. There is a x part and a y part, or an input and an output. So given this relation of these three set of ordered pairs, what we want to do is identify what is the domain and what is the range. We know that domain is all our x's or inputs, and range is all our y's or our outputs. So we want to list what are all the x values for our domain. In this relation, that would be 1, 3, and 5. Our range is the set of all the y's. So in this example, it'd be 2, 4, and 6. So domain and range, those are your x's and y's, your inputs, your outputs. All right, so moving on, what we're going to be looking at more specifically today, and this is where the new stuff is what is a inverse relation. And an inverse relation is the set of ordered pairs found by reversing the x and y values. So anytime you switch around or reverse the x and y, you come up with a function that is the inverse. So using the example we were doing a little bit ago, we are going to figure out what is the inverse relation. So we have the same example. The inverse would be obtained by switching all our x and y. So we're going to reverse those. So the inverse relation for the first order pair would be 2, 1 if we switch around the x and y's. We're going to do the same thing with the other ones, 4, 3, and 6, 5. And that would be considered the inverse relation. So switch or reverse the x and y. All right, let's look at another example. In this next one, so a new set of ordered pairs are given for a relation, and they are the vertices or corners of a right triangle. They want us to find the inverse of this relation and then graph both. So here's what we're going to do first. Well, let's find the inverse. What would be the inverse relation? Remember, you do that by switching the x and y's around. So if we switch around our first ordered pair 2, 1, we'd get 1, 2. Let's do the same with the next one. 1, 5. And finally, our last one would be -4, 2. That is our inverse relation. Now we're going to graph both the relation and its inverse. Starting with the first relation, we're going to graph that over on our coordinate plane over here. So the point 2, 1 is located there, the point 5, 1, and the point 2, -4. Connecting those, we get our right triangle. All right, now we're going to graph the inverse. So we're going to graph all our inverse relation ordered pairs. Point 1, 2, point 1, 5, and the point -4, 2 also forms a right triangle. What we have here is then both the original relation and its inverse. Anytime you graph both the relation and its inverse, it ends up being a reflection. Recall from geometry reflections where you take a shape and flip it over a line of reflection. Anytime you graph a relation and its inverse, it's always a reflection over the line y equals x. Now the line y equals x, we'll graph that on here to kind of show you that it is actually a reflection over that line. The line y equals x is a linear line. There is no number listed in front of x, but we know anytime that there's no number listed, there's a 1 there, 1 over 1. And there's no y-intercept listed, so it passes through the origin. So if we graph that line, up 1 over 1, up 1 over 1, it forms this 45-degree line that passes through the origin. Now, if you look at our graph and its inverse, you can see, yes, it is a reflection over that line. Every vertice is equally distant away from that line of reflection and perpendicular. So anytime you graph a inverse and its relation, it always is a reflection over the line y equals x. All right, in the next set of notes here, another notation for inverse if you're dealing with functions is that if you have a function f of x, the inverse is f of -1 of x. This -1 is the notation for inverse. A function and its inverse will always give you the opposite point of an ordered pair. So if you plug in A and the result is B, that means you have the ordered pair AB. Then the inverse function, if you plug in the y value, should give you the x value. Let's look at an example. On this one, it says find the inverse of the function f of x equals x plus 2. Anytime we do an inverse, we said we want to flip around the x and y. Well, in function notation, you don't really have an x and a y, but we know that f of x is the same as y. So if we flip around x and y, we will get the equation x equals y plus 2. Okay, the x becomes y, the y becomes x. If we solve this now for y, we will have it in, we will find the inverse. So what we're going to do is solve this little equation for y. The only thing we need to get out of there is this 2, so we're going to subtract it since it's being added. If we do that, now we end up with y equals x minus 2, and that then is the inverse. So y equals x minus 2 is our inverse function, or if you write it in the function notation, the inverse function is x minus 2. All right, now what we said is if we are to take the inverse and plug it in, we should get the opposite value. So here, let's take our original function, f of x equals x plus 2. Let's see what we get when we plug in 5. If we plug in the value 5, we get 5 plus 2, which equals 7. So that means there's an ordered pair, 5, 7. If we do the inverse, we should get the opposite value. So if we plug in 7, we should get 5. Let's check and see if it works. So our inverse function that we just got was, the inverse is x minus 2. Let's see what we get when we plug in 7. So 7 minus 2 equals 5. Yes, we get that opposite value of 5, 7. So these would be inverses of each other. All right, let's try some other examples. In the next one, number 2, a little more complicated, but again, they want us to find what is the inverse. So again, our f of x is like our y. We're going to switch around x and y. If we solve for y, we should get the inverse. All right, so on this one, we should notice first that this function is being divided by 2. We don't really like fractions, so let's try to get rid of the fraction. If we're dividing by 2, the opposite would be to multiply by 2. Those 2's cancel out. Now we're at 2x equals y plus 6. Next step, we want to get y by itself. Let's subtract that 6 out of there. And now we get y equals 2x minus 6. That then is our inverse. So our inverse is y equals 2x minus 6. Or again, if we write it in function notation, the inverse function would be 2x minus 6. So that would be the inverse function. I want you to try number 3 for tomorrow. See if you can find the inverse of that one, and we'll check and see what you got tomorrow. Let's move on to number 4. On number 4, they want us to determine whether these two functions are inverses or not. One way you can check to see if they are inverses is to use composition. We talked about composition yesterday. Composition is where you plug one function in for another function. So we're going to see what is f composed with g equal. We're also going to check what is g composed with f equal to. If they're inverses, we should get the line of reflection when you have an inverse. Recall our line of reflection, anytime you do an inverse, is that 45-degree line, y equals x. So if these truly are inverses, we should get x when we do the composition. So let's try it out. Let's start with f composed with g. So function f is 3/4 of something minus 6. We're going to plug in function g in for x and see what we get. So if we plug in function g, we get 4x plus 8. All right, so we're going to simplify this. Start out by distributing. If we multiply 3/4 times 4/3, those are reciprocals of each other. It's going to equal 1. So we get 1x, or just x. We also need to take 3/4 times 8. 3/4 times 8 is 6. Simplifying, we get x. Well, we're off to a good start. We said we should get x if they are inverses of each other. But we got to check the other one too, because sometimes it doesn't always work the other way. So let's check the other one. What do you get when you take g composed with f? So if we plug in function f for g, 3/4 x minus 6, we should simplify and also get x. Again, distribute. If we distribute, 3/4 times 4/3 x is going to be 1x, or just x. 4/3 of 6 is 8. If we simplify, this one also equals x. So yes, these are inverses. These are inverse functions. All right, let's look at an application. On this next problem, we want to find the inverse of this equation. And if you look, this is the formula for the area of a circle. Area equals pi r squared. They want us to find the inverse and see what is that. So basically, what would be the equation if instead of saying a equals, what would it be if we solved it and got it so it said r equals? So what we're going to do is solve this for r. All right, so what do we got to do first? We got area equals pi r squared. To get r by itself, we want to get rid of everything on the side with r. We want to divide, and we're going to divide by pi. Remember, pi is like a number, even though it kind of looks like a variable. We're going to divide by that first. So now we got area over pi equals r squared. Oh, I still got to get rid of that power of 2. To get rid of a power of 2, we want to take the square up. So if we square up both sides, now we got the equation r equals the square root of a over pi. And now that would be the inverse. Now we got an equation that says r equals instead of a equals. Why is this useful, or what could we do? Well, now we could answer a question like with the second part of this question. They want us to use the inverse of the radius to find the area of 314 centimeters squared. So if we want to figure out what the radius is, all we got to do is now is plug in this area. So radius equals square root of area over pi. If we plug in this area of 314, we can figure that out. So we got square root of 314 divided by pi. If we take square root of 314 and divide it by pi, you're going to get something pretty close to 100. And if you take the square root of 100, the answer is going to come out to be pretty close to 10 centimeters. So now we know what the radius of that circle would be. All right, we're going to finish the rest of this worksheet when you get to class, but now you got a little introduction to inverse.